Is it a bird, a plane, or a paramedic? Yep, that's the one. Here in the Lake District, it can sometimes be difficult for them to get to someone who needs help quickly, even if they use helicopters. But the Great North Air Ambulance Service is hoping that with a jet suit like this, journeys that would usually take around 25 minutes on foot would be cut to about 90 seconds. It wants to launch the world's first jet suit paramedic.
I guess it's a drone.
Richard Browning used a jetpack he invented for a special test flight.
The jet suits, they work by using pretty much the same things that you have on a jet aircraft. Two on each arm, one on the back, and the way that they then blow so much air downwards allows you to then lift off the ground. And then all the maneuverability is actually down to using your own natural human balance and coordination.
The pack can fly for around 5 minutes at a time, but most journeys would be much shorter than this. And Richard says it's also safe for the person flying, even if something goes wrong. The ambulance service hope that with some changes to the design, they'll be able to get paramedics flying up the mountains by next summer.
All right. So, no idea. He looks like he's got some gas cylinders on the back, so it could be propane. It might be jet fuel, right? It seems like little jet motors, but I'm not sure whether you can make them quite so compact. It's kind of cool. I remember seeing at the Bastille Day celebrations in France, one of these, but with a guy with a rifle. Clearly it was a military application for the same deal. But anyway, so but it's quite cool. All right, let's do this. You'll no doubt be disappointed not to hear the music on this. It's kind of oompa music, but you've seen this before, and I think you understand the rationale of what we've been talking about for the last little while. On Monday we were talking about material derivatives, and so we made the point that it matters what your frame of reference is as to how you evaluate relative velocities. The velocity that you see that jet going at is different from someone who's standing at the front of the boat firing that jet of water. And that's important in terms of defining accelerations relative to static or moving reference frames, which is really what the material derivative is. And the second thing we did on Wednesday was we said that we're going to start talking about conservation equations and looking at conservation of mass first this week, which we'll finish today, momentum next week, and then kinetic energy the following week. And so that's kind of a central part of what we're doing. And of course, the conservation of energy part kind of intersects with the stuff in thermo, if you're taking that, because it's the ability to be able to get energy out of chemical reactions as well, although we won't talk about that in this class per se. So that's kind of where we're going with this. And so maybe we'll come back to that picture again. I don't really have any announcements for the good of the order, but we're 6 weeks in. We'll be at the end of 6 weeks today, so you're 6/15ths of the way through the class. The presentation stuff is due, I think, next Wednesday. So you'll get another email at midnight tonight to tell you what is on the horizon. There are no review sessions, there's no midterms in clear sight, but the Wednesday deadline is for the presentation titles if you haven't already put it up. It's a pretty soft deadline, I think. It's not a deadline like the homework deadline, which is kind of firm, and the midterms deadlines. So if you're having trouble getting with your group, I guess you have two options. Decide on your topic and just ignore the people that don't respond to you. Do it with the cadre of people who are with you. Or I know that did Jai do this? Jai took two groups where they had perhaps two people in each group who are busy trying to get hold of people. The other people didn't respond, so she put the movers and shakers together and put the non-movers and non-shakers together. And that's probably not a bad solution. So if you need that at some stage, then Jai is coordinating this. I don't know if she'll send out an email, but certainly in my email tonight, it'll give you the Wednesday deadline. And she did send out an email telling you how to get physically hold of your groups. And by the way, if you send an email to them through Canvas, for some reason I also get it. I don't want it, but I get it. And so don't say, well, that slacker Ellsworth told us we should get together, so let's get together and make a group me. You can leave the first part out. Because I don't know why I get it. There's no reason why I should get it. And I don't know whether you know whether I do or not. But everyone's been the picture of decorum so far. So that's kind of where we are. The Wednesday deadline, I don't think is a hard deadline. Maybe if Jai comes back to you and wants you all to have a different presentation from each other, then the first people to lodge that presentation, I guess, would get precedence. I don't know that's relevant anymore. We used to do these things in the class, so people came to class to view it as an audience, and it was live. It was interesting to see some of the dynamics. I remember one group coming up where they physically didn't allow one person to join them because that person wasn't allowed to speak because that person had done nothing. And so kind of interesting group dynamics. And so in the evaluation of your presentations, I would say they're kind of generously graded, loosely graded. I'm not sure how you say that. If you do a good job, I think you can get a pretty close to full score. The split is that it's 85% of a score and 15% peer review. And so the one place where you have an opportunity to be able to make a comment about the people who did or didn't produce, if you're in that situation, it's in there. And so that's the deal for that. And so that's coming up on Wednesday. So as I say, maybe good to get it in. It's a relatively soft deadline, though. Okay. All right. Well, welcome here on a Friday. As is our plan in the past, or our custom, we'll talk a little bit about where we've come from. And I suppose, and I will repeat again, I don't know if I get this. Yeah, I can pull it up. And so the first point is related to this. And I don't know if I want to make it a full. And so the idea is that when we look at conservation equations, we look at material derivatives for a reason, because we have to take account of the kind of reference frame in which we find ourselves. And so that's maybe one thing that we have to account for in this. You remember that we talked about this. That's the picture rather than the video. This is the video. And so what we'll do today is we'll talk about this behavior that we broached on last time. And what I'd like to do is try and solve this problem, a very simple problem, using the three different approaches we talked about. We talked about the pipe, the jet engine, and the balloon that represent a kind of a static, non-deforming reference frame, a moving, non-deforming reference frame, the jet engine, and a deforming and moving reference frame, the balloon in that particular case. And so we'll attempt to do that today with what we'll do. So let's go back to our stuff. And I will say that I'm going to do this in a much more simple way than I've done in the past. So if you want the gold standard version, last year's video for 6.3 is there. I'm not sure exactly whether people take on the complicated way, and I think I have an easier way to explain it today anyway. And so I'm enthusiastic to be able to share that with you. So what do we talk about? We talked last time about the idea of conservation of mass. If we use Reynolds transport theorem, we can apply that to any quantity. We chose to apply it to mass, which is represented by this term B, which comes to be 1 in each of these cases. B is just mass divided by mass. This term on the left-hand side is 0. And you don't need to know that. What you need to know is what this looks like. And the equation that we will use is this. And so it relates to accumulation. So the left-hand side is accumulation. Perhaps I can write that. So this is accumulation. Plus mass out minus mass rate in, actually, it's mass rate in, equals 0. That's the physical meaning of this expression. This term here is this. This term here is this. So am I using a a blunt instrument. It seems a bit more blunt than normal. And so this can be written as this. So this is the expression that you'll use. And you'll notice that we have taken this velocity here, and we've replaced it with a W. And so that's the one thing we do. So these are standard: time, density, density. This is a velocity. This is a relative to the boundary velocity we'll talk about. We talked about this being a dot product, which is just gives the sign to this that accounts for the mass in or mass out in this, and this is over an area. And so the easiest way for you to think about this is to draw it as we did on Wednesday, and that is that you have a control surface, which is the surface that you complete this integral over. That surface encloses a control volume, which is the area volume inside it, because it has a distance into the page. And we would like to be able to look at the velocities coming out of it and the velocity of flow into it. The dot product that we have here is represented, making this, is that if the flow is out, then it's parallel to the normal to the boundary, as we talked about last time. This is the unit normal. And so these are congruent with each other. So this is, in my parlance, positive out. And it's negative in. Oh, that's my son saying rabbits. Does anyone say rabbits, rabbits, rabbits? First of the month? Yeah, same deal. You saw it here. Good luck for the rest of the month if you say that before you say anything else in the morning. Good superstition to have. So this is a velocity out, and so the mass rate of flow out would be equal to the velocity relative to the boundary times the area times the density, quite literally. So that's what this is here. Density, velocity, area. This is a mass rate, kilograms per second. And the sign of it depends on our knowing whether it's out. So if it's out, will always be perpendicular to the boundary. The dot product allows you if it's inclined. I'm not sure we'll do anything like that. And so we can get that. The other components are that we can split this term here. Actually, I'm going to run out of time. I'm going so slowly with this. Is that we can split this by the product rule. So if I use the shorthand that rho dot is equal to rate of change, so it's a standard convention, is rate of change of density with time. So this is just a sidebar here. So we can split this up as rho dot times volume plus volume dot, rate of change of volume times density plus this summation equals 0, right? So we can split this left-hand term up as these. And so this allows us to accommodate the fact that the density could be changing, pushing air into a tire. The tire volume doesn't change very much, but certainly the density of the air changes. Or you're filling a beaker. So the density of the water doesn't change because it's incompressible, but the volume of the control volume, which might be the whole surface of the water as it goes up, does change. And so I guess we should mention that each of these is that if you look at, for these systems, time versus volume. So in other words, if you're filling a beaker, then the volume of the beaker increases with time. So positive is if V is increasing, right? Just sign conventions we're talking about so far. And I guess the other one would be that if you're pushing air into a tire with time, then density would do this, and this again is positive. So if density increases with time, it's positive. If volume increases with time, they're positive. And that if flow is out of the system with time, it's positive. We just have to account for those conventions. And so it'll appear normal when we do these things. So that's the first part. The second part is that we magically changed this velocity here to a relative velocity. And so we've just looked at the boat. I love drawing this boat. Here we go. This is my fire tender. Oh, it's fantastic. And this fire tender is moving with some velocity of the control surface, and it's squirting water out of the control surface at some rate W. And so if you combine both of these together, and I draw it here, then if you're standing on the dock and watching this, then you see the boat moving at 1 meter a second. You're squirting water out at 1 meter a second. So the velocity to a static observer is 2 meters a second. That's what you see. Boat's moving, squirting. You sum those, it's a vector sum. These are vectors. And so actually it's not just a magnitude in the x direction, but there'd be x, y, and z just as well. But let's just think of it as one for now. Let's not worry about the fact that they're vectors. And so we can write from this always, because they're vectors. If we take these two together, that velocity static is equal to the velocity of the control surface plus the velocity coming out of the system. So we could, I suppose, running out of colors, but I could use something nice here. We could also draw a control volume around here. So this is the control volume that we're looking at. And so really, if you're squirting water out of here at 1 meter a second, or if you're squirting water out of here at 1 meter a second, it doesn't matter what the boat is doing. If you're looking at the control volume being the boat, if you have 10 kilograms of water in the boat and you're squirting it out at 1 kilogram per second, then it'll take 10 seconds to deplete. And it doesn't matter if the boat's going in any particular direction or you're squirting in any particular direction, you'll deplete the mass within the boat in 10 seconds, either way. And so, all by making the point that the reason that this W is here instead of this velocity here is that it makes sense that if you're conserving on a control volume, so if this is our control surface here, this magenta line, if that's what it is, then it makes sense that we do the relative to the control volume velocity in depleting volume from that control volume. Right? That's all we're saying. And so this table merely makes the case that this is what the behavior should look like. I can get rid of this right-hand side, I think. And that is, we have these three different cases. Remember, we talked about the pipe. If I can draw it like this. We said that we could take a section of the pipe and have a control volume in it. And that this was static and non-deforming. In this case, the control surface is moving at a velocity which is 0. And because it's non-deforming, staying the same size, the volume with time is not changing either. This is V dot, uppercase V dot. If we have a moving and non-deforming one, well, that, if I can draw it, is my jet engine. Then this isn't changing size, but it's translating. And so clearly, I should have drawn it the same. I don't know why I drew it that way. This is the velocity of the control surface. And it's actually the velocity of the control volume, right? Because the control surface at the front is moving at the same rate as the control surface at the back, because this is not concertina getting larger. So really the velocity of the control surface has to be the velocity of the control volume. Kind of semantics maybe, but so. And of course, non-deforming, so it's not changing volume with time. And then the one that I draw least best is this balloon that's floating around the case. It's moving for sure because you've let go of it. It's deforming because it's losing mass. And so the velocity of the control surface is different from this potentially, because the velocity that this is going at, this part here, might be different from the velocity that this is going at the back, because it's shrinking at the same time. So if it's shrinking 1 millimeter a second and it's moving forward 1 millimeter a second, then the front might be moving at 1 millimeter a second, but the back might be moving at 2 millimeters a second because it's shrinking and catching up, right? So maybe it's semantics, but the velocity of the control surface is not zero, and the volume change with time is not zero. So the other thing is that this idea here kind of plays into what we'll do, because this is the expression that we've written down below in green. And if we wanted to, since we've said that it's important that we define our behavior in terms of the relative to the boundary velocity, we might want to rewrite this equation in this way for some reason. And so we'll need these concepts when we talk about the other conservation, and we'll use them today just to illustrate exactly what I'm trying to say. So that's where we're going. So let's do something with this instead of just talk about it. So what I plan to do is to... Is this writing big enough now? Yeah, plenty big enough for you. Is to use that. So what am I going to do? All right, so what I'm going to do is I'm going to take the geometry that we looked at, and I guess maybe, yeah. So this is the problem geometry. So it's a beaker. And in the geometry that you saw of the glass, you have a jet of fluid coming down and slowly filling up this volume. And so that's the one we looked at, but that's just too difficult. And so I'm going to translate that into something that is equivalent to that, but different. And equivalent to that because it is... don't know why it's not doing that. Is I'm going to fill it from the bottom. And so I'm going to fill it from this, with fluid coming up into it, and the fluid comes up at some velocity v1. It has a surface in it, which is this surface here, and I'm going to have a height which is h0. I'm going to have an area a1, which is the area of this jet. Remember, the other one was difficult because not only is it coming down and we have to deal with that, but remember, as it comes down, it tapers because the water accelerates as it comes down. So we get rid of these problems just by filling up the beaker from the bottom. We have some height to this, h. We have some area of the bucket, and we use that to be able to write our equations. So you'll be sick of this equation. Well, you might be sick of it already, actually. But this is necessary for us to write. So that's the expression we have. So what do we have in this particular case? I guess I did that wrong, so let me get rid of that. One of these needs to be a rho dot, right? Change in density. So what do we have going on here? It's water coming into it. So the change in density is probably going to be trivial, so we can probably get rid of some of these terms. This term is going to be 0, we don't care. We have water coming in through the bottom, so we worry about that. And we have a rate of change of volume that's occurring. So the volume, depending on how we draw our control volume, is going to change. And so we need to be able to take care of this. So if we want to solve the problem of how long does it take to fill this container, what do you do to do that? Well, I guess it's probably easiest to write this as, if you know what the volume of the bucket is, and you divide the volume of the bucket by the rate at which you fill it, this is equal to a time, right? This is volume per time. 1 over time is this. So you have a 10-gallon bucket, you pour in a gallon per minute, it takes 10 minutes to fill. That's all that is. And so that is the easiest way to do it. And so in this particular case, the volume is equal to, so this would be in very simple terms, the volume is going to be equal to A2 times H. The volume rate is going to be equal to V1 times A1. And that's your answer. So we're going to do this problem multiple ways, and we should always end up with this intuitive answer that you've already got. That should be A2H times V1A1. So we start off with an amount in there just because it's easiest for us to do that. But the time it takes for us to fill the rest of the thing is going to be this amount of time here. So what we could do is we could divide this up into if I draw a line here to cap it off. So we're going to do each of these. This one, and this one. So static non-deforming. What does that physically look like? Let me draw the container. I'm going to draw the container now in isometric, in this. So this is how high the water is up to, this is H0, I guess, what we've called it. This is going to be the rate at which we put water in. So over a portion of this, we have water going in at some rate, V1. This length here is A1. And this surface here is rising at some rate. And so what do we want to do? For the first of our conditions, we have, this is going to be blue. So this is 1. So static non-deforming. Takes me a long time to write. So let's draw a control volume. Do I want to chance it with this? I guess I could do. Let me chance it with this. Oh, it doesn't work very well. So that's our control volume. So we can write our expression if we like for that. And our expression is going to be, I don't want to do that. I guess I want to switch back to this. So what do we have? Rho V dot plus V rho dot plus sum of rho W areas equals 0. What do we have going on here? Well, we clearly have a couple of things going on. We have some fluids coming out of the top of this volume at some rate, right? This is our control, I guess I could label our control volume. This is going to be V2. This is going to be area A2, if you want to put that there. It's not really the cross section, right? Because it's an area, not a length. And so this is just the answer that we already had. So if you write the rate of change of volume is going to be 0 because it's static. I guess I missed out some letters. The rate of change of density is going to be 0. And it's going to be just the sum of these two components. So if we write this out in longhand, it's going to be quite simply rho V1 A1 plus or minus rho V2 A2 equals 0. What's the sign convention? Flow in is negative by our convention because of what we said about this boundary here. This is the normal. So this is going to be negative V. Flow out is positive for the same reason. So this is going to be positive. I'll get rid of that. And so we can get rid of the densities if it's not compressing. So V1, A1 is equal to V2 A2. And so we can just use that to be able to define V2 is equal to V1 A1 over A2. And how do we calculate how long it takes to fill? Well, we can do it in terms of a velocity, right? This is h. So velocity is equal to length over time. So length, so I guess we should rearrange that in terms of time. So time is equal to over v, this is velocity, and so length over velocity is equal to time, and so we can do that in terms of this. Length time is equal to h over v2, right, because it's this length coming up here, and it should be equal to time is going to be equal to h times h. V2 is going to be equal to V1 A1 over A2. And hopefully that looks like this, right? So the intuitive way that you to solve this is exactly what this gives you in the velocity of this coming out of this standard control volume. It doesn't solve this directly because you have to calculate for how long it would take to rise up here, but that's the result that you get. So that's the first of our problems. So the second is moving and non-deforming. So let me see how clever I can be with this. If I can do this. So let me copy. Oh. I can actually do something for once. So let's see. All right. So let's get back to this. So I guess this is number 2. So this is moving, but not deforming. So let's see how we do this. Can let me see this. No, let me see this. All right. Ah, perfect. God, I'm so pleased with myself. So let's see if we can draw this same container, but with something else done. And so this is a non-deforming container, so it has to have the same control volume, but what this container can do is it can physically float up to the top of the bucket. And so that's what we're going to allow it to do. And so it'll start off at this point here, but it will have some velocity, and that velocity moving up will be the velocity of the control volume, which is equal to the velocity of the control surface. So remember, my volumes always have a bar through them, so these are velocities. So this is going to be moving up. And so the best way you can think about this is froth on a glass of beer, or glass of soda if you prefer. And so this is going to move up, and it's going to be tagged to the top velocity of the water, is our easiest way to do it. And so if we write our expression for rate of change density times rate of change of volume plus volume times rate of change of density plus, let's write it out in terms of rho W1 A1 plus rho W2 A2 equals 0. then we can look at what these individual terms are. So remember, this is floating up with the top surface as it rises. So what does that mean? Well, it's non-deforming first. So this has to be 0. The fluid is a liquid, and so it's not changing in density in any significant manner. It's not like putting air into a tire. And so we have to worry about these components. This is really going to be the relative velocities. So if I draw this control volume, let me draw it in the same color at least. So if I draw this control volume that we have here, that is moving upwards with this velocity of the control surface, then what are the velocities? So this is A1 on the bottom and A2 on the top. Actually, this is A2. And the reason that this is written this way is that I said that this is floating to the top. So what's the relative velocity of W coming across this boundary? Well, clearly, if it's floating to the top, then the velocity of that top of the control volume, which is the top of the froth on your beer, is rising at the same rate. So this W1 has to be equal to 0, because it's floating up with the froth. The froth isn't coming above the control volume, so the velocity has to be 0. Likewise, fluid is coming into here at the bottom as it moves up, and so there's no ability for that fluid to go in there. It's gathering below it, down here, but it's not making an incursion into here. So the velocity across this boundary here also has to be 0. I guess this is W2, right? This is this one. So this is 0. But for the same reason as that, the water coming up here is just displacing this whole control volume upwards. And so the velocity here, 1, is also equal to 0. And so it doesn't really matter what this is, but this has to be A2, right? It has to be the whole volume of the whole area of the bottom, not just the spigot that's coming in here, but the whole volume, because this thing's traveling up. It's traveling up and translating. You can think of it like a float sitting on top of water that takes up the whole, a polystyrene float that sits on the top of this fluid that rises with the whole thing. And the control volume is that volume of the float, and it's just kind of moving up. So by definition, these volumes must be 0. And so this equates to 0, but that's not very helpful. And so it's not very helpful because you have to then use something else to be able to define this behavior. And I guess we need to define this behavior in some other way. And the only way we can do it is to be able to figure out exactly what V2 is. And so we can't do it from this. So this doesn't become very useful anymore, even though we've used it. And the way that we solve it would be to be able to write a conservation equation on the fluid that's coming in here. And we know that V1 A1 equals V2 A2 from our previous ones. We could pre-multiply by density on both sides, it doesn't matter. And we again get, for instance, V2 is equal to V1 A1 over A2. And again, we have to use this expression here, that T is equal to length over velocity, which is equal to the length it needs to travel, which is h, divided by its velocity, which is v2, which is equal to h times a2, this term here, right? a2 v1 a1. And so, not surprisingly, since it's the same problem, we end up with exactly the same result. And we end up with the same result here, as we end up with the same result here, as we end up with the same result if you do it the way that you just think about it in terms of how long does it take to fill a bucket. 1 kilogram a second, 10 kilogram capacity bucket, takes 10 seconds. That's all we're doing. And so I guess you could write this instead of length over velocity. If we wanted to, we could also write time is equal to length over velocity. We could also multiply both top and bottom by area 2 and area 2. And this would be a volume, and this would be a volume rate. Again, just as we talked about up here. You know, how you do it. Mass rates or volume rates. If the density is not changing, then we don't have to worry about it. Okay? So it becomes a bit academic at some stages, but let's do the other one as well. So we talked about 3 of these particular ways of doing it. And believe me, if you think this is complicated, look at 6.3 last year and see if you want to, if your head explodes based on that. Okay, I'm going to be fancy again. Is it worthwhile me trying to copy these, just like I did last time? I guess it'll move some of it down. Some things that we don't want moved down. Okay. And again, see if I get rid of the control. So, all right. Where's it gone? So, the third one is going to be, what is it? What order do we put it? So, it's moving and deforming. So, for this, what are we going to do? So we're going to do the same as before. I'm going to draw myself a nice little box around it. And so this box is now going to be different. So, okay, so this is the box at how it starts. But instead of translating upwards, it's going to do this. It's going to grow with time as it goes upwards. And so physically, it's going to be anchored at the bottom. And so I guess we have to be able to define what the behaviors are. This is going to be the velocity of the control surface. The velocity of the control surface here is 0. The velocity of the control surface on the other sides are 0 as well, but we don't care about those. And so it's going to grow from this magnitude here up to this. And so again, we have to write that same expression. So what is it? Density times rate of change of volume. You should write it the same each way. Yeah. Times rate of change of volume plus volume times rate of change of density plus W1 A2 rho plus W2 A2 rho. I deliberately put A2 there, is equal to 0. And I'll draw the box separate from itself. Just to get an idea of what's going on. And so it's quite straightforward. I say everything's straightforward. This is the velocity of the control surface. This is the velocity of the control surface, which is equal to 0. And we can look at the relative velocities of the fluids. So the fluid is coming in through the bottom. And so we can look at that fluid velocity here. And so what's that going to be? So this is 0 because nothing's happening. The velocity here is going to be into here. It's going to be W1. Actually, I don't want that to be. I made a big point of making the case that I wanted that to be A2, but I don't. What's going on? A1. And so this is going to be, this velocity here would be what we called V1. So this would be just V1 before, A1 and density. What is the velocity on the top surface going to be? Well, again, this is moving with exactly the same velocity as the water. It's the top of the froth on the beer, and so it's moving up. So W2 has to equal 0 for the same reasons as it had to be in this particular case, which I've erased because it was translating up as a float. In this case, it's translating up, but it's stretching the volume. And clearly, this is not going to be 0. So this is not equal to 0. And so we end up with an expression which is density times rate of change of volume plus V1 A1 rho. This is a velocity into it, and so if we draw our unit normal outwards, don't have to do this, then this is negative, so that just means that this velocity is negative and it's equal to 0. We could probably, I don't know why I'm changing colors, we can probably get rid of the densities. Update canvas, that's for me to make sure that the email that you get, are we going over? No. The email that you get on midnight on Friday is actually correct from change from last year. And so in other words, the volume change is equal to V1 A1, because this is a negative. What's volume change? Volume change would be area 2 times V2, right? So an incremental amount of, if you think about the change in volume, it's this amount here, and that's given by this surface going up at velocity V2 and making a new volume, which gives you this length. So this length here is equal to V2 A2 times T, right? So that's what this length. So the so this is this. We got rid of this. This is volume change. So area times velocity per unit time. Oh, velocity is per unit time. And so if we rearrange that, how do I want to do that? Use V1 A1. Yeah. V2. So V dot. So stop doing that. This is V2, right? By definition, this is this. And so there's no reason why we can't combine these two. I guess that's the same thing. And so V1 A1 equals V2 A2. And so V2 is equal to V1 A1 over V2. And we know that time is equal to length over velocity, which is equal to, the length has to be h2 divided by v2. And if we take this down here, this is equal to h2 v2 v1 a1. Okay. QED, quo et demonstrandum, right? So this is the same result as we had before. And of course that should be the case. Hopefully V2 is the same. There's no H. V2, V1, A1. And so I guess the point that we've tried to make, or I've tried to make, is that irrespective of how you solve this problem, it's physically the same problem. There's no doubt that that's the case, right? You're filling up a beaker or a bucket from the bottom, incongruous in some respect, but it's physically the same problem. We can represent it in a variety of different ways to be able to describe that problem. And no matter what way we describe it, as it should do, the solution, since it's a physical problem, has to come out to be the same because we're solving the same problem at the same time. And so that's the way of dealing with it. If you want to have a more complicated way of doing these, well, you can see what these are. I don't think this is the stuff that we've basically done in these 1.5 pages. It's the same idea and a couple of examples which I won't go through. But that's all we'll do in talking about conservation of mass. So it allows us to be able to define rates at which it takes to fill volumes. Sometimes you'll use that in conjunction with conservation of momentum to be able to solve things, but this is all that we'll talk about in terms of conservation of mass. So I hope that was relatively straightforward. So anyway, so that's it for today. I guess the next assignment, again, is live. You have the material now to do it. Next week we'll work from the same principles in that we'll use this kind of unwieldy thing called Reynolds transport theorem, but instead of conserving mass, which we've done today, in kind of different reference frames, we'll start talking about conservation of linear momentum to be able to conserve not mass, but mass times velocity. And so it becomes a bit more complicated because mass, of course, is a scalar quantity. It just has magnitude. Momentum is a vectoral quantity that has both magnitude and direction, mv. And so it becomes a little bit more taxing, but the same principles apply, and we'll work on those next week. Okay? Thanks very much.